Okay guys, we already did a lecture on the work of a point charge distribution. Now we're going to think about the work of a continuous charge distribution, where the learning outcome is to calculate the energy to assemble, not just bring point charges together, but I actually want to assemble some kind of continuous sheet of charge, a sphere of charge, something like that. If I'm pushing charge together, okay, if it doesn't want to be together, or pulling it apart if it wants to be together, depending on whether there's a repulsive or attractive force, then I am storing energy in the charge distribution. Okay, so let's think about that. We're going to start out with our formula for point charges. And that tells us that the work that we did to assemble a system is equal to that 1/2, which is important, don't forget that, times the sum from I to N of Q, that's the charge, right, that I'm trying to do the sum over, times the potential at the final location of that charge due to all the other charges that are around it. Okay, so now I want to do this for our funky charged object. Okay, and remember, when we have these little charged objects, we think about breaking them into little infinitesimal bits of charge, little dqi's. Okay, and so we can think about how we can turn this sum into an integral, okay, by taking that chunks of charge and making them very small, and then, right, distributing them continuously. Okay, so the sum, it turns into an integral over a bunch of our little infinitesimal bits of charge. Okay, so that turns our sum into something that looks like, right, the potential, oops, let me do this a little again. The potential at our charge positions, which is where we get that prime, times dq, our little chunks of charge. So I'm going to say that the prime says we are referring to where the charge is. Okay, so we're throwing the prime in there. Just like we did our other volume integrals, I can replace this dq with a rho times d tau if it's a volume, or I can replace it with a sigma dA if it is a surface charge, or I can do lambda dl if it's a line of charge. Okay, so that gives us, the most general form is going to use that volume charge. That gives us a equation to calculate the work of the system that looks like the integral of our potential evaluated at a particular point times that charge distribution, okay, which could also depend on R, times our volume. And we're going to do that volume integral over, right, the whole funky charged object. Okay, let's think about this another way. Another way that is also useful here, right, we have to know what the potential is and what the charge distribution is. So maybe we want to come up, refer ways to finding the work if we know something else about our charge distribution, like the electric field. Let's recall that if I do it this way, which is what I just wrote out, okay, let's transform this integral a little bit. I'm going to let rho be equal to the divergence of the electric field times epsilon naught. That's going to give me that this integral is going to be equal to epsilon naught over 2. And now I'm going to be integrating the divergence, okay, times my potential times d tau. Okay, I'm going to skip a big spiel here on integration by parts, but that's what we're using now, and I recommend that you guys look it up in the book. If you want to pause the video right now, you can. Okay, but I'm going to use integration by parts to rewrite this integral into something that initially is going to look more complicated, but then we're going to simplify it a little bit. Okay, so this integral I can write here as two terms. The first term is going to be the electric field dotted with the gradient of my potential. Okay, this is equal to the electric field, right? Okay, times d tau. Okay, and by the way, when I dot the electric field by itself, you end up just getting the magnitude of the electric field squared because this dot product is going to turn these two vectors into a scalar and they're pointing in the same direction. So I get the full magnitude. Okay, and then I'm going to take a surface integral over a closed surface of the potential times the electric field dotted with our area vector. Okay, so let's rewrite that one more time since we did a little bit of simplification. That's just going to be e squared d tau plus this guy here. Okay, let's think about how we can simplify this even more. All right, so we can do these integrals here. If I look up here, it's important to note, okay, that I just need to integrate over all of the charge. I can't miss any of the charge to calculate the work to assemble. Okay, so I need to make sure that whatever this volume integral is, it surrounds all of the charge here. Okay, but if I go down here, okay, I can integrate with any volume as long as it surrounds the charge. Okay, if I pick a big volume, what's going to happen is this term is going to get bigger because it's a volume integral. So I'm going to be summing up the electric field squared over that entire volume, which is going to make this term bigger. But as this term gets bigger, this term is going to get smaller because this is a surface integral. Okay, and I'm just going to be integrating the potential times the electric field, which are decreasing with distance over that surface. So they actually balance each other out. Okay, so the changes in this one and the changes in that one as I choose different surfaces, they're going to balance out and they're always going to be equal when I sum them together to the same thing. Okay, so I'm going to choose a really big surface. Okay, if I choose a really big, which means basically an infinite surface, okay, then I can actually simplify this integral. This is our volume integral over e squared d tau plus our surface integral. No, that is not what okay, and this one is going to go to 0. And the reason is because v and e go to 0, okay, at infinity. Which is to say, again, as I change the size of my volume, this is going to get smaller, this is going to get bigger, but they're always going to sum to the same value. So really I'm just cheating to simplify this integral. It would still work for any volume, but I want to simplify it. So I'm just going to do this integral, okay, but the way that I have it written out, I've got to integrate over the electric field over all space. Okay, so this has to go over the limits have to go over all space, okay, which basically means to infinity and negative infinity and things like that. Okay, I'm not going to do an example here for time, but I would like you guys to gander example 2.9. Okay, and then just one more note. I'm going to rewrite this as e squared epsilon naught over 2 d tau. And I want to note that this stuff in the middle, this has units of energy over volume. Okay, so I can quantify this new thing, this 1/2 e squared epsilon naught is something called energy density, and it's the amount of energy stored in a parcel or a volume of electric field. Okay, so basically it's saying is how much energy is stored in a volume of electric field. So that's pretty cool. That really, like, if we go back to the beginning, that really shows us that the electric field is a real object. If I just have an electric field in space and I separate, I think about just some volume of that field, just that volume of field is storing energy.